Good day, everyone. Welcome to this session. I am tasked to provide you a comprehensive lecture on the introduction of organic chemistry. I am Mr. Wences G. Gerdose, a faculty member from the Science Department of the College of Arts and Sciences, Guimaras State College.
In this video, we will tackle the concepts of organic chemistry. Perhaps we have already encountered organic chemistry in our undergraduate courses, and we all know that organic chemistry is the chemistry of compounds of carbon. That means carbon is the prime actor in organic chemistry. Carbon is capital letter C in our periodic table, and it is the sixth element in the periodic table. The name carbon is derived from the Latin carbo, meaning charcoal. As what I've said earlier, we have already encountered organic chemistry. Thus, we know that organic compounds are everywhere around us. So they are in our foods, flavors, and fragrances, in our medicines, in our toiletries and cosmetics, in our plastics, films, fibers, in our paints, varnishes, and glues, and of course, organic compounds also found in our bodies and the bodies of all living organisms. This illustration here provides us an idea of a complex metabolic pathway that is usually occurs in our living system. As what you have observed, on the topmost, we have proteins, polysaccharides, nucleic acids, and lipids. These are macromolecules. Macro means these molecules are huge enough or big enough. Thus, our body needs to break these macromolecules into simpler one through, of course, these metabolic pathways. In biology, metabolic pathways are very important for us to obtain energy in the form of ATP or adenosine triphosphate, or in layman's term, energy. Perhaps the most remarkable feature of organic compounds is that they involve the chemistry of carbon and only a few other elements, chiefly hydrogen, oxygen, and nitrogen. While the majority of organic compounds contain carbon and just these three elements, many also contains sulfur, a halogen which includes fluorine, chlorine, bromine, or iodine, and phosphorus. Now the question, why is organic chemistry a separate discipline within chemistry? So the first reason is largely historical. In the early days of chemistry, scientists thought that organic compounds were those produced by living organisms, and that of inorganic compounds were those found in the rocks and other non-living matter. At that time, they believed that a vital force possessed only by living organisms and was necessary to produce organic compounds. In other words, chemists at the time believed that they could not synthesize any organic compounds by starting with only inorganic compounds. And This theory was very easy to disprove if indeed it was wrong. It only required one experiment in which an organic compound was made from inorganic compounds. Like what you have observed in the slide as of the moment, the production of urea and silver chloride. The urea is considered as organic compound because it contains carbon in the structure. In 1828, Friedrich Wöhler carried out just such an experiment. He heated an aqueous solution of ammonium chloride and silver cyanate, both inorganic compounds, and to his surprise, he obtained urea, which is an organic compound found usually in our urine. A second reason for the study of carbon compounds as a separate discipline is the sheer number of organic compounds. Chemists have discovered or synthesized more than 10 million of them, and an estimated 10,000 new ones are reported each year. By comparison, chemists have discovered or synthesized an estimated 1.7 million inorganic compounds. Thus, approximately 85% of all known compounds are organic compounds. A third reason, and one particularly important for those of you going on to the study of biochemistry, it is the biochemicals, including carbohydrates, lipids, proteins, enzymes, nucleic acids, which include the deoxyribonucleic acid and the ribonucleic acid, or the DNA and RNA, hormones, vitamins, and almost of other important chemicals in living systems are organic compounds. One final point about organic compounds is that they generally differ from inorganic compounds in many of their properties, some of which are shown in the next slide. In general, here is the comparison of organic and inorganic compounds. So, in this portion, we have organic compounds that has a bonding which is almost entirely covalent, while for inorganic compounds, most have ionic bonds. And many of organic compounds are gases, liquids, or solids in low melting points, which is less than 360 degrees Celsius, while inorganic compounds, most are solids with high melting points. Most of organic compounds are insoluble in water, while inorganic compounds are soluble in water. Most of organic compounds are soluble in organic solvents such as diethyl ether, toluene, and dichloromethane, while inorganic compounds almost are insoluble in organic solvents. Most of organic compounds are aqueous solutions, do not conduct electricity, while in organic compounds, their aqueous solution forms ions that conduct electricity. Almost of organic compounds are burned and decompose, while inorganic compounds, very few. While organic compounds also reactions are usually slow, and inorganic compounds, the reactions are often very fast. After we compare the properties of organic and inorganic compounds, the next question is, where do we obtain organic compounds? So chemists obtain organic compounds in two principal ways. One is the isolation from nature, and number two, synthesize in the laboratory. When we say isolation from nature, so living organisms are chemical factories. That means each terrestrial, marines, and freshwater plants and animals, even microorganisms such as bacteria, make thousands of organic compounds by a process called biosynthesis. One way, then, to get organic compounds is to extract. Extract, that means we remove from the living system. We extract, we isolate, and purify them from biological sources. One important example of isolation of organic compounds from nature is the vitamin E, or the isolation of vitamin E. The penicillins, table sugar, insulin, and anti-cancer drugs, which is the Taxol. These compounds are isolated and extracted from a living source or from a biological source. And as of today, nature also supplies us with three other important sources of organic compounds, like natural gas, petroleum, and coal, which is very important in our day-to-day living. The second one is we synthesize organic compounds in the laboratory. Ever since Wöhler synthesized urea, which is the organic compound, and Wöhler, he is a organic chemist which have sought to develop more ways to synthesize the same compounds or design derivatives of those found in nature. In recent years, the methods of doing so have become so sophisticated, and there are few natural organic compounds, no matter how complicated, that chemists cannot synthesize in the laboratory. Compounds made in the laboratory are identical in both chemical and physical properties to those found in nature, assuming, of course, that each is 100% pure. There is no way that anyone can tell whether a sample of any particular compound was made by chemists or obtained from nature. So, as a consequence, pure ethanol made by chemists has exactly the same physical and chemical properties as pure ethanol prepared by distilling wine. The same is true for ascorbic acid, or also known as vitamin C. There is no advance, therefore, in paying more money for vitamin C, which is obtained from a natural source, than for synthetic vitamin C, because the two are identical in every way. And it is also convenient for us to obtain vitamin C in a capsule than to pick some of citrus plants and squeeze it for our juice. But we do not end up there. Organic chemists, however, have not been satisfied with merely duplicating nature's compound. Usually, organic chemists have also designed and synthesized compounds that are not found in nature. In fact, the majority of the more than 10 million known organic compounds are purely synthetic and do not exist in living organisms. For example, many modern drugs like Valium, albuterol, Prozac, Zantac, and Viagra, which are synthesized in the laboratory, and these are considered as synthetic organic compounds that are not found in nature. Even over-the-counter drugs, aspirin and ibuprofen, are synthetic organic compounds that are not found in nature. The next question that we need to answer is that how do we write structural formulas of organic compounds? So a structural formula that is shown in the slide is known as the structural formula. The structural formula shows the atoms present in a molecule as well as the bonds that connects the atoms to each other. So the structural formula that is shown there shows the connection of different elements to your carbon. And the Lewis model of bonding enables us to see how carbon forms 4 covalent bonds that may be various combination of a single, a double, and a triple bonds. Furthermore, the valence shell electron pair repulsion, or the VSEPR model, tells us that the most common bond angles about carbon atoms in covalent compounds are approximately 109.5 degrees, 120 degrees, and 180 degrees for tetrahedral, trigonal, planar, and linear geometries, respectively. So the table shows there that several covalent compounds containing carbon bonded to hydrogen, oxygen, nitrogen, and chlorine. From the left side is the ethane, which has a bond angles about 109.5 degrees, showing the connection of carbon to hydrogen with a single bond. Also, we have ethylene, which has 2 carbons, double bonded, and a connection to hydrogen. Regarding with the structural formulas of organic compounds, there are several rules that we need to comply. So, among neutral or uncharged organic compounds, for example, we have carbon. Carbon usually forms 4 covalent bonds and has no unshared pairs of electrons. That means carbon can form 4 connections. Hydrogen forms 1 covalent bond and no unshared pairs of electrons. Nitrogen normally forms 3 covalent bonds and has 1 unshared pair of electrons. The oxygen normally forms 2 covalent bonds and has 2 unshared pairs of electrons. And halogens normally forms 1 covalent bond and has 3 unshared pairs of electrons. Again, when we say halogens, these are fluorine, chlorine, bromine, iodine. As we go along towards the end of our lecture, the last question is, what is a functional group? As we already discussed, what is organic chemistry? How do we write the structure of, or what is the structure of organic compounds? Where do we obtain organic compounds? Now, let's focus our attention on functional group. We all know earlier that more than 10 million organic compounds have been discovered and synthesized by organic chemists. It might seem an almost impossible task to learn the physical and the chemical properties of so many compounds. Fortunately, the study of organic compounds is not as formidable a task as you might think. So that means functional groups are very important. While organic compounds can undergo a wide variety of chemical reactions, only certain portions of their structures undergo chemical transformations. We call the atoms or groups of an organic molecules that undergo predictable chemical reactions as a functional group. Again, a functional group is an atom or group of atoms within a molecule or in an organic molecule that shows a characteristic set of predictable physical and chemical properties. These functional groups are very important so that we can group our organic compounds. Functional groups are important because they undergo the same types of chemical reactions no matter in what organic molecule they are found. To a large measure, they determine, of course, functional group determine the chemical and the physical properties of a molecule. Functional groups are the units by which we divide organic compounds into families. And functional groups provide the basis on which we derive names for organic compounds. That is why when we study organic chemistry, we need always to identify the functional groups because functional groups is very important, particularly in naming organic compounds. So in this table gives us the 7 common functional groups. We have different families here: the alcohol, the amine, aldehyde, ketone, carboxylic acid, ester, and amide. So for alcohol, the functional group is OH. Okay. For amine, the NH2. For aldehyde, the C double bond OH. For ketone, the C double bond O, or C is double bonded to oxygen. Carboxylic acid is C carbon double bonded to oxygen and single bonded to OH. Ester, C double bonded to oxygen and C single bonded to OR. And amide, C double bond O and H2. So by understanding and familiarizing the different functional groups, we can identify the family of organic compounds. Soon, as we go along with our lectures regarding with families of organic compounds, we will understand the different structures, naming, and at the same time their reactions. Of course, then using the different functional groups of organic molecules. At this point, our concern is simply pattern recognition. That is why how to recognize and identify one of these 6 common functional groups when you see it, and how to draw the structural formulas of molecules containing them. As what I have said earlier, the functional groups also serve as the basis of naming organic compounds. Ideally, each of the 10 million or more organic names of organic compounds, we must have a unique name different from the name of every other organic compound. Now, first we have an alcohol. As previously mentioned, the functional group of an alcohol is an OH, or also known as hydroxyl group. So in alcohols, the hydroxyl group is bonded to a tetrahedral carbon atom, a carbon having bonds of 4 atoms. In the general formula of an alcohol, the symbol R indicates either a hydrogen or other carbon group. And the important point here of the general structure is the OH group bonded to a tetrahedral carbon atom, or the hydroxyl group. Again, alcohol contains OH group, or known as hydroxyl group, that is bonded to a tetrahedral carbon atom. What do we mean about tetrahedral carbon atom? This is a carbon atom that usually holds 4 bonds to different atoms. As what you observe here on the right portion, we have the condensed structural formula of an alcohol, represented by CH3CH2OH. In the condensed structural formula, the CH3 indicates a carbon bonded to 3 hydrogens. The CH2 indicates a carbon bonded to 2 hydrogens, and the CH indicates a carbon bonded to 1 hydrogen. Unshared pairs of electrons are generally not shown in the condensed structural formulas. Below, alcohols are also classified as primary, secondary, and tertiary alcohols, depending on the number of carbon atoms bonded to the carbon bearing the OH group. Again, when we classify alcohols, if it is primary or secondary or a tertiary alcohol, we always depend our classification on the number of carbon atoms bonded to the carbon bearing hydroxyl group, or the carbon that bears the hydroxyl group, or the OH group. In this example, it is considered as primary alcohol because the CH3 here is bonded to your carbon that bears the hydroxyl group. When we count how many carbon bonded to your carbon that is attached to your OH or hydroxyl group, only one carbon. Thus, it is considered as a primary alcohol. Here, in this illustration, we can observe that here is the carbon-bearing hydroxyl group, and we count how many carbons attached to this carbon. 1, 2. Thus, we considered it as secondary alcohol. And the third one, we have 3 carbons bonded to the carbon bearing the hydroxyl group. Thus, this is tertiary alcohol. Remember the R group in our previous slide? The R group here is an abbreviation of any group of atoms that may include carbons, hydrogens, halogens, oxygens, and nitrogens that are attached to a functional group or represent a side chain to the rest of the molecule. In this slide, we observe here the R. R, it's either a hydrogen or a carbon group. Again, R group, it is an abbreviation of any group of atoms that may include carbons, hydrogens, halogens, oxygens, and nitrogens that are attached to a functional group or represent a side chain to the rest of a molecule. In the midst of the pandemic, we are experiencing the pandemic, the COVID pandemic. We are usually using 2 types of alcohols, which is readily available in the market. One is the ethyl alcohol or the ethanol, and another one is the 2-propanol, or also known as isopropyl alcohol. These alcohols available in the market are used to disinfect cuts and scrapes in our skin. An amine. So, an amine is an organic compound in which 1, 2, or 3 hydrogens of ammonia are replaced by carbon groups, which is the RNH2, the R2NH, or the R3N, or the NH2. Basically, when you observe these structures, these are amino groups. And these amino groups, if these amino groups are attached to your carbon, then therefore it is an amine compound that compose or contains amino group. Amino groups as primary, secondary, and tertiary, led to 2 hydrogens and 1 carbon group, which is a primary amine. By definition, a primary amine, the nitrogen is bonded to 2 hydrogens and 1 carbon group. In a secondary amine, on the other hand, it is bonded to 1 hydrogen and On the tertiary amine, it is bonded to 3 carbon groups. Carbon. That is why it is considered as tertiary amine. In this case, this compound is trimethylamine. That means the nitrogen has 3 methyls attached on it, while in this dimethylamine, which is a secondary amine, only 2 methyl attached to your nitrogen. Here, it's methylamine or a primary amine because CH3, which is methyl, is attached to nitrogen. Thus, again, it is a primary amine. Aldehyde and the ketones. Remember that aldehydes and ketones are different families, but they have the same functional group, which is the C double bond O, or also known as the carbonyl group. Again, aldehydes and ketones contains carbonyl group or the C double bond O. When we are talking with an aldehyde is a compound containing a carbonyl group bonded to a hydrogen. Again, aldehyde is a compound containing a carbonyl group bonded to a hydrogen. Or we should write the functional group of aldehyde C double bond O and the H, or this one. Now, before we go onto the structure, let's have ketone first. Ketone, on the other hand, contains a carbonyl group bonded to 2 carbon atoms. Okay, in terms of the structure, when we're talking with aldehydes, we observe this C double bond O. But since it is an aldehyde, there is an additional hydrogen. In this structure, this is an example of a ketone, which the C double bond, or C is double bonded to oxygen, or the O, but the C is also bonded with another carbon. Thus, it is a ketone. It is classified as ketone. Again, aldehyde, C double bond O and then H, while ketone, C double bond O, C. That makes differ from an aldehyde. An example of an aldehyde containing C double bond O, H is an acetaldehyde. And for a ketone containing C double bond O, CH3 is acetone. And ketones has carbonyl group or the C double bond O. But the difference between aldehyde and ketones, the carbonyl group of aldehyde has hydrogen, while the carbonyl group of ketone has carbon, a carboxylic acids. The functional group of a carboxylic acid is COOH. COOH, or also known as the carboxyl group. Again, the carboxylic acid is a compound containing a COOH, which is also known as the carboxyl group. Why it is carboxyl group? Because it is a combination of a carbonyl and your hydroxyl group. Remember, in our alcohol, the functional group is OH, or the hydroxyl group. While in our aldehydes and ketones, it is your carbonyl group. In carboxylic acid, we combine the carbonyl and the hydroxyl group. Thus, we call it carboxyl group. The carb of the carbonyl and the oxyl of the hydroxyl group. The group may also be written as CO2H. In your basic chemistry, we all know that this subscript 2 signifies 2 oxygen that is bonded to your carbon. Okay? So, the functional group, if we write it in a structural formula, we have the R. Remember the R in our previous slides. It is a group, either CH3 or a hydrogen that is attached to your carbon atom. Your carbon here, your C, is double bonded to oxygen. That is your carbonyl, right? And your C is also attached to your oxygen and hydrogen. That is your hydroxyl group. As what I've said earlier, carboxyl group is a combination of a carbonyl group and a hydroxyl group. As you remember our previous slides, your OH or your hydroxyl group is present in your alcohol, and your carbonyl group is also present in your aldehydes and ketones. One example of your carboxylic acid is your acetic acid. Your acetic acid is the CH3 attached, of course, to your carbonyl group, which is the C double bond OOH. A carboxylic ester is commonly referred to as simply an ester. An ester is a derivative of a carboxylic acid. Again, it is a derivative of a carboxylic acid in which the hydrogen of the carboxyl group is replaced by a carbon group. So the ester group is written either COOR or CO2R in the text. In our previous slide, the hydroxyl group here, okay, the hydroxyl group is actually attached to your O. That's in your carboxylic acid. Since it is a derivative of a carboxylic acid, the hydrogen of the carboxyl group is replaced by carbon. Let's try to look into this. This is the functional group of carboxylic ester. Supposed to be, if this is a carboxyl group of a carboxylic acid, it should be written as C double bond O O H. Since carboxylic ester is a derivative of a carboxylic acid, wherein, supposing this is the hydrogen, it is replaced by a carbon group. Thus, it gives us a carboxylic ester, or we call it simply an ester. Example of an ester is methyl acetate. As what you observe, the C double bond O, O attached to C. This is a carboxylic ester. But if this is a carboxylic acid, the formula is C double bond O, O, H only. Your carboxylic amide. Your carboxylic amide, or known as an amide. Your amide or carboxylic amide, in which the OH of the carboxyl group is replaced by an amino group. Previous slides, that an amine, it contains an NH2, or it contains a nitrogen. In this case of carboxylic amide, since it is a derivative of carboxylic acid, instead that the carboxyl group or the OH of the carboxylic acid or of the carboxyl group is usually replaced by an amino group. Let's have this example. We have the acetamide, which is a primary amide. Supposing this is a carboxylic acid. Since this is a carboxylic acid, it should be C double bond O, OH. Okay? Since we are assuming that it is a carboxylic acid, it is a C double bond O, OH. But this is a derivative of a carboxylic acid, which is an amide. As what I've said earlier, an amide has NH2 or an amino group instead of hydroxyl group. Again, your acetamide, supposed to be, if this is a carboxylic acid, the functional group of your carboxylic acid is C double bond O, OH. But since this is a derivative, which is a carboxylic amide, the OH here is replaced by amino group, which is NH2. That is why it is said to be a carboxylic amide, which is a derivative of a carboxylic acid.
That ends our lecture for today. Thank you everyone for your kind attention. God bless.